Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is in our dynamic series. The major category is Kinematics of Particles, subtopic, Rectilinear Motion. Stay tuned if you want to find out what that means. If you need more help, or if you want practice problems for this, I recommend you secure a good dynamics book, inexpensive one. Some good choices here, and we're going to utilize figures from a few of these. We've got Beer and Johnson, great book, listed down here below, sections 11 and point 1 and 3. Merriam and Craig, also great book, or Gray, Costanzo, and Placia. Three great books that are used. Beer and Johnson is probably the most widely used. Merriam and Craig is actually a good book. Doesn't have quite as many tricky problems as Beer and Johnson. And Gray, Costanzo, and Placia has some really key insights in a few sections I've found. So these books can help you if you need more help. Let's take a look at the primary principles. We're going to be looking at kinematic relationships. These sound kind of overly complicated, but these can be used. So you got to remember, mathematics is just a tool. It's like a pistol in the hand of a cowboy, or a shovel in the hand of a worker, or a hammer and nails, or electric tools. Mathematics is the tool that we use to process the information we see and how things work on this earth and in the nearby solar system. So kinematic relations will help us. We can look at the trajectory of a golf ball, of a satellite, of aircraft, all kinds of things. The key is right here. This may feel painful as we go through some of these ideas the first time and when you're struggling on a test or something, but these ideas can help you to master these concepts so you can unravel the mysteries of the universe. And it's much easier than it appears once you begin to master it. Okay, so stay tuned and let's take a look at some of the fundamental concepts. So in a simple sense, we can say that kinematics is the study of geometry of motion. So we're going to relate displacement, that's where we are and how we're moving, right? Displacement, which is position, velocity, acceleration, and time. So displacement is basically position. Velocity is how fast we're moving. Acceleration is how our velocity is changing, and all of these relating to time of when these things are happening is how we're going to tie this together. Now, kinematics is the study of the relations between forces acting on the body, the mass of the body, and the motion. So we can predict what's happening in the kinematic world by studying the kinetic world, where we're looking at the forces relative to the masses. These are the keys that we're going to be orchestrating to solve these kind of problems, okay? So for an aircraft, we've got thrust, and that thrust is resisted primarily by drag in the horizontal realm. If we have more thrust than drag, we're going to be accelerating. If we have less thrust than drag, we're going to be decelerating. If we have equal amounts of thrust and drag, we're going to have constant velocity motion. Now we also see the lift force, and what we don't see here is the weight of the aircraft. So the weight of the aircraft and the lift are the two countering forces for vertical flight. So if our lift is greater than our weight, we're going to have a vertical acceleration. And if our weight is greater than our lift, we're going to have a vertical deceleration, or we're going to be accelerating downward. Okay? All right. So those are our basic ideas. If we want to make this really simple, we could kind of say, since kinematics relates, we're looking at what's the displacement, what's the velocity, and what's the acceleration. We don't care why. We could kind of say that this is like the magic, the hocus pocus part of physics, the kinematics. The kinetics is more like the science of physics, because what we're doing is looking at the causes of what's happening. In kinematics, we're just looking at what's happening. We're here, we're here. Our velocity is this, our acceleration is this. In the kinetics, we're saying, why did this happen? Well, we had a unbalance of forces which cause accelerations, and that's why we had changes in our velocity and position and things like this. If you want to make this even simpler, stay tuned. We could say, all right, if we want to understand the difference between kinematics and kinetics, we could say, okay, oh, look, there's a little boy running across a screen. Isn't that nice? That's kind of like kinematics, where we're studying where is he at a particular point in time, what is his velocity at a particular point in time, and how is he accelerating. Kinetics is more like the why of why he's running, right? The kinetics just looks at where is he, what speed, what acceleration, who cares why. The kinetics is more like the why, where we say, oh, look, we've got a monster chasing him. That's causing an unbalance of force and causing those changes in the kinematic relationships. Okay, put grossly simply. All right. That we could say that's kinetics, evaluating his motion without worrying over its cause, and the kinetics is the studying of the forces that cause that. All right. We talked before in our first lecture about particles and how basically with particles we're just saying whatever it is, we're pretending it's so small that its size doesn't affect anything, whether it has mass or not. Its size doesn't change. Like we could treat it like a little tiny point in space. And we're going to study a lot of the ideas as a particle because it makes it simpler and often is sufficiently accurate. Okay, so here we're looking at a three-dimensional system of space, right? We've got X, Y, and Z. We could call it 1, 2, 3. And we have some kind of body out there. We're going to say it's a particle, and that particle has motion. We could say that it has a position, like we could talk about rectangular coordinates, X, Y, Z of that point. We could talk about polar coordinates like R, theta, Z. So R, the radius, the angle that it's at, and then the elevation, or spherical coordinates where we're talking about the R, the theta relative to the R, and then the phi, that rotation in the other direction. So we're going to be studying out, we're generally going to use rectangular coordinates whenever we can, or whenever it's simplest. Often it will be simplest to use rectangular coordinates for many engineering problems, because even though we're on a curved Earth, we can often treat it as flat for our purposes, analyzing locally. We start getting into space and we'll start to need to use cylindrical or spherical coordinates, and there's certain kinds of problems that are going to lend themselves to easier solutions when we're using cylindrical or spherical coordinates. You as students will typically be more comfortable with rectangular coordinates because we have more experience and it makes more sense to us a lot of times. And we're going to tend to shy away from the polar and spherical coordinates. However, just like I said before, mathematics is a tool. These trigonomic systems are not that difficult, and actually choosing the appropriate system can make your problem a lot easier, or even make it solvable where it would otherwise be unsolvable. So we have to master all three types, and we also need to develop the judgment to choose which is the easiest coordinate system to use for a particular problem. Is it rectangular coordinates? Is it cylindrical coordinates? Or is it spherical coordinates? Most of our early stuff will be rectangular, and we'll dabble in the others as we are developing the ability to handle that. Okay, so rectilinear motion. So what that means is we have a particle moving in a straight line, okay? Now rectilinear just basically means linear motion in a rectangular coordinate system, which basically involves a straight line. So if we look at this line segment, like back in first grade or whenever we learned that, we could say, oh, look, we have a particle at point O, or we have an origin at point O. We have a particle out here at some distance from that point along this axis. We could call this axis X for the X position, or we could call it, a lot of times we use S for position, which is a more generic and general way of describing position. But in this particular case, since we're talking rectilinear, we could just lay our axis, our coordinate system, right on the x-axis. We could say, oh, this particle is at 1, 2, 3, 4, 5, position 5, which might be 5 inches, 5 meters, 5 feet, whatever. Okay? In this case, it looks like it's meters. So the particle is at 5 initially, right? And if we talk about how it moves, we could say, okay, is it moving at a different time? Is it the same point or a different point? If it's to the right at a higher number, that has a positive motion or a negative motion going the other way. Okay, so our position coordinate, we're going to have to get comfortable talking about things in terms of their position, where we can just talk about the X or the S. X being along the X-axis, Y being along the Y-axis, or maybe it has an X and Y coordinate as a function of time in a two-dimensional system, or even an X, Y, Z in a three-dimensional system, okay? So our motion can be evaluated if we understand what the position is at different times. So in this particular case, we're looking at a particle. Initially, it was a 0.5 meters to the right of the origin. At another time, it's 2 positions to the left of the origin. So it went from +5 to -2. So what we're going to do is learn the kinematic relations that relate those 2 positions, so we can determine, okay, if we know what the time was here and the time was here, we can calculate what the velocity is and things like this, okay? So we're going to be plotting the position and time is one way of doing this. We could plot the position versus time. For example, X position versus T time. You can see that it's changing, it's speeding up and then slowing down. So our motion can be determined if we can write the equation for what this is, or even evaluate numerically discrete positions. For example, one type of equation we might see is X equals 6t squared minus t cubed. This says, okay, this is the equation relating position to time. That means we can just plug in any time, like 0, and we find that the particle is at 0. If we plug in 10, we then solve this equation, plugging in t equals 10 seconds, and we can calculate what the position is at 10 seconds. Or we could plot it continuously as we see here on the left. Okay, so this is the plot. Now, we're going to be looking at, this is our position versus time, and we're going to be studying out also velocity and acceleration as we move forward. All right, so let's just go back to this. If we say, okay, our particle is at this first position at time t, and it's at a different position at time t at some other time, which we're going to say t, the time it was, plus some change in time, okay? So the change between these is delta t, okay? And our change in position is delta x. Our average velocity is that change in x with respect to the change in time. So dx dt, or delta x, delta t. That is our velocity. Got that? So dx dt, that's our average. Why do we say it's the average? Because actually, in order to get there, that particle might have gone tearing forward, come back a little bit, sped up, slowed down, you name it, stand by. So the velocity might have changed going from this position to this position. It's just like when you're leaving your house. You go out the door, you get in your car, you drive down the street, you said, oh, I forgot my keys to the house. I go back to the house, I get the keys. I go even faster the next time, I say, oh, I forgot my hat. You go back. You could have had all kinds of different velocities going between your first position and your second position. If you just look at position, change in position versus time, change in time, all you're getting is the average velocity, which could include big numbers, little numbers, and even negative numbers. The instantaneous velocity will be that change in distance with respect to change in time as you make that change in time smaller and smaller and smaller and smaller. So in the limit, you're going to end up having, when t is 0 on the bottom, you're infinite. But as that gets smaller and smaller, you're actually looking at that instantaneous change, that change in velocity in position versus change in time. That will tell us at any particular moment what our time is. If we think back to the definition of a derivative, that's just the derivative. That means we can just take the derivative of the equation that relates position to time, take the derivative of that with respect to time, and we can figure out what the position is, okay? Or, excuse me, we can figure out what the velocity is, right? The derivative of dx dt is the velocity. Got that? Okay. Our instantaneous velocity can be positive or negative. The magnitude of the velocity is called speed. It's just another word for velocity, but usually we say the magnitude of it is speed, and the velocity actually could be considered a vector. Okay? Therefore, as we said, that from the definition of a derivative, the velocity is just dx dt. We just take the derivative of x with respect to t and get the velocity. For example, our early example, if we have position was given as a function of 6t squared minus t cubed, we just take the derivative of that, and that may drop the 2, that's 12t, drop the 3t squared, and that gives us our velocity. We could actually plot that out as a function of time, as we see here on the left, and we can evaluate our motion. Okay? Now, a lot of students don't really enjoy the plotting part. A lot of this, we're just going to be plugging in numbers, looking at this position versus this. We'll just get magnitudes of values, but sometimes it's useful and necessary to plot these, and you want to develop that skill as well. Okay? All right, so far we've got these relations. We've got our velocity. It's just the change in position with respect to time. Now, we've been looking at this as dx dt. But remember, x is just meaning we're lying on the x-coordinate. That could have been lying on the y-coordinate. Could have been lying on the z-coordinate. Could have been the dr of dt, or d theta dt, or d phi dt. So as a more general variable, we use s as the position variable a lot of times. So we can say ds dt, which is this change in position, which can be in a one-dimensional, two-dimensional, three-dimensional system, you name it. If we look at that change in position, ds, with respect to the change in time, dt, that is the definition of velocity. We can actually use this equation, and we're going to, backwards and forwards. We can use ds dt to get velocity, and now we can integrate this puppy, as we're going to see in a moment, to calculate what the position is from the velocity and the time. So once again, if we rearrange this, bring the dt over v dt, integrate both sides, the one with respect to s, the other with respect to t, we now have a simple relation that we can calculate what the position is by evaluating the velocity and the change in time. Or we can evaluate what the velocity is by evaluating the position with respect to time. Or sometimes even we can calculate what the time change is by evaluating the change in position with respect to its velocity. So one of the hardest parts of dynamics and also statics is not so much remembering what the equations are and how they relate, but it's evaluating these equations backwards and forwards, and also combining them and rearranging them so we can relate position, time, and acceleration. Okay? And velocity. So if we have a constant velocity, so if v is constant, that comes out of the integral. Now ds is just s2 minus s1, right? Because it's just an s, but going from s0 to s1. So s2, we're saying that we're going from 0 to 1 instead of 1 to 2. We could have said 1 to 2 just as easily. So if we're going from 0 initial to 1 the next time period, then actually when you integrate that left side, you're going to get an s, and it's going to go from s0 to s1, which means s1 minus s0 equals the integral, and the velocity came out of that integral since it's constant, of dt, which is just a t, but that's going from t2 to t1. So now we end up with s minus s0. We called it s1 before, now we're just calling it s. The position at the next time is just, we bring that s0 to the other side of the equal sign. We're left with that v and the t going from t1 minus t0. So t, we could plug in the 2 time periods. So whatever the change in time, that looks like a t here, but that's the change in time going from the t1 minus t0. That's what is in that little piece there. So these are common equations. We're going to use these backwards and forwards. Remember, this last equation is only valid when the velocity is constant. If it's not constant, it may be changing such that it's not just quite this simple. Okay? All right. Let's look at acceleration. We're still talking about rectilinear, which means one-directional motion. And we could say, okay, we got the particle at the one position, the particle at the other position. It had a velocity before, and it has a velocity, a different velocity at the next time that we look at it. So we have v, the initial velocity, and we have v plus dv, which means we have the velocity it was plus some change. So really going from the one to the other, it's just dv is the change. But it had a velocity before, and it has a new velocity now. So we could say this is t plus delta t. We could say this was at v, this was v plus delta v, and we have these two positions, which we can call 1 and 2, or 0 and 1, or you name it, okay? So we've got a particle. It has a velocity at the initial time t, and at some later time, t plus delta t, it has a velocity. Our instantaneous, so once again, the average acceleration will just be evaluating the change in velocity with respect to time, same way we did before. But if we want the instantaneous acceleration, then we just make that limit at that delta t, make it smaller and smaller. So we say, okay, let's see. At today, we're at a certain velocity, and 20 hours later, we're at another velocity. If we look at the change in velocity divided by that time, that gives us that average acceleration. Have the same problem we had before. If we want the instantaneous acceleration, what we need to do is reduce that time span. So we're going from like t of 1 from 0 to like 1 second. That gives us still the average velocity from 0 to 1, but that average, it wasn't changing very much between there, which is almost like it's a constant. It's a lot easier to evaluate how that changed, okay? So by shrinking down the time, we actually get the instantaneous acceleration as we move along. If we just look at just dv dt, that's giving us average. Okay? dv dt is giving us the average, but if we take the limit of that, as the limit as the t delta t gets smaller and smaller, we're going to get the instantaneous acceleration. Okay? So, for example, now, our instantaneous acceleration, it might be positive, which means between the two times we're looking at, it's going faster and faster. Our velocity is increasing. It might be negative. We might, at one point, we might have two different velocities. This one, we might have a decreasing velocity. If our velocity, if we had a negative velocity, like we're slowing down, and even we have a slower slowing down, that's actually two negatives makes a positive. That's going to give us a positive acceleration also. Negative means we've got a decreasing positive velocity or an increasing negative velocity, right? Two wrongs make a right, two negatives make a positive. Okay? So once again, from the derivative, the definition of a derivative, we can just take the derivative of dv dt, and that gives us acceleration. For example, we go back to our last example. If velocity is just 12t minus 3t squared, all we have to do now, take the derivative of that puppy, and we're going to get that instantaneous acceleration. Or actually, the equation of that acceleration, we can plug in any value of t, and we will get the acceleration at that particular point in time. You got that? Okay. So here's our key relations that we've been talking about. Our acceleration is just the change in velocity with respect to time, dv dt. We can integrate that, bring the dt to the other side, integrate both sides, right? And that will give us the change in velocity. We can either integrate the acceleration, or we can take the integration of the dv and solve this. So this can relate our velocity to our acceleration and our time. We can take the derivative of velocity to acceleration, or the integral of the acceleration to get our velocity, okay? Once again, this left side, this is just v, right? When we take the integral of dv, we're going to get v, and that means v1 minus v0. Often what we'll do is we'll then bring that v0 to the other side of the equal sign. We'll say the v at the new time is that initial velocity plus whatever we get from the right-hand integration, okay? If our acceleration happens to be constant, we're going to look at this kind of problem a lot. A lot of problems can be simplified this way, and it's mostly true, where we can pretend that the acceleration is constant. We'll bring it out of the integral, and we're going to get v equals vo plus at. Remember, we have v2 minus v1, or v minus v0. We brought the v0 to the other side. We took the integration. The a came out of the integral. The integral of dt with respect to t is just t. and that's just t minus t0. So also recalling that our velocity, our position is just the integral of the velocity, we can now integrate that puppy, and this gives us the relation that we can get the position at any time by taking the original position, the original velocity, multiplied by the amount of time, the acceleration that you have, or average acceleration, times that time squared, 1/2 of that. By integrating this, we get this relation. Remember, this is for constant acceleration. This is for constant acceleration. These up here will work for anything. These lower two equations are only if the acceleration is constant. Okay? We can also say, all right, since our acceleration is the second position, it's the second derivative of the position with respect to time. Since our derivative of position with respect to time was velocity, our derivative of velocity with respect to time is our acceleration. That means acceleration is the second derivative of the position with respect to time. And sometimes writing in that form will help. We can also use this intermediate kind of equation. The velocity times the change in velocity is equal to acceleration times the change in acceleration. This just goes back to, this is just combining these two relations, and we get this relation. We'll be using that as well. Okay? All right, so we can look at, it's helpful to maybe think about this a little further of acceleration and how it relates. Remember, I said before, one of the hardest parts of dynamics is keeping track of when we use which equations and how we put them together, which ones we pull out first, what do we plug into those. And the biggest inhibitor to this is, well, the first one is ignorance, when we haven't learned it yet, and the second one is fear. Once we start learning the principles, our fear tends to keep us from implementing them. You probably have already experienced this, where you think you know what you need to do, but you're afraid to go, and you don't want to, you're lazy too, right? So you don't want to take the time to work it out because you're not sure it's the right approach. You need to drop that, courageously run forward, and be ready and okay with having to erase and redo. That'll make you be able to solve this a lot faster if you show a little courage in your analysis by being willing to invest time on slapping wrong answers on the page while you develop the judgment to solve these efficiently. Okay? So let's just take a look at it. We've got, okay, we can have acceleration written as a function of time. Okay, that's our first category here. If we have that relation we just talked about. The acceleration is just the change in velocity with respect to time. This is going to give us the acceleration as a function of time. And we can integrate acceleration to get that velocity. Okay? Now the other way, also relating acceleration, we could have acceleration as a function of x. Like, hey, we've got the position here, we've got the position here. If we have the acceleration written as a function of x. So how does that work? We think, okay, well, let's see. Remember, our velocity is just the change in position with respect to time. So we could write that as, rearrange that by saying then, by bringing the dt to the left and the v to the bottom, that means dt, the change in time, is just dx over v. We already know that the acceleration is dv dt like we saw before. We can combine these two by plugging in the dt, and we can get this new relation, which is actually not new at all. It's just like mixing a little creamer in your coffee, whoever wants to do that nonsense. And we can write this relation, which is often very helpful. The velocity times the change in velocity is equal to the acceleration as a function of x times dx. This is often going to pop up as being the equation we're going to want if we have acceleration written as a function of position rather than as a function of time. And then we can integrate that puppy to as well. Okay? Or we can have the acceleration written as a function of velocity. At one velocity we have an acceleration, another velocity we have acceleration. When that happens, we can say, all right, let's go back to our relation dv dt is equal to the acceleration. That means we can integrate, we can rearrange and integrate like this. dv over the acceleration with respect to v is the integral of dt. So these are giving us different variants of the same equation, because acceleration is a function of time and position and velocity. And you can get it by evaluating position with respect to time, or velocity with respect to time, or velocity with respect to position. All these different ways. And that's what makes it harder, because there are different ways we can do it, and we develop the judgment to choose the way that gets us there faster, or in some cases, the only way that can get us there. Being comfortable with writing the acceleration as a function of time, or position, or velocity. We're usually not necessarily writing it that way, but identifying, oh, the pieces of information we have are velocity and acceleration, therefore, we're going to use this third method. Or we have position given, we're going to have that second method, or acceleration in time, okay? So that's the basic ideas we're going to be playing with. The key to learning this is first to go through the lecture and kind of get a feel, a general feel for the principles. You're going to feel like, yeah, I think I have it. You're going to have a little fear, a little confidence, false confidence. You really don't need to not believe you've mastered this until you've done some homework, and the more homework problems, the better. As I've said in another video and in my classes, lectures are kind of like chewing food. It tastes really good. When you first start chewing, you got the best flavor. If you chew too long, the food gets bad in your mouth. But when you first start chewing on a new food, it's so flavorful and you feel like you've got so much nutrition. But you actually have negligible nutrition, negligible sustainable energy until you swallow. Swallowing makes that food, puts the food in a place where your body can utilize it and turn it into energy. And homework is like the swallowing. Lectures are like the chewing. So you need to do sufficient homework problems. And you can get any of those books, the Baron Johnson, Miriam and Craig, or even the Gray, Kuzansko, and Placia. I call it Placia usually. Any of those books or any other standard dynamics books, there will be tons of problems, many of which with answers in the back. You could practice on these, and it's those homework problems in these sections where you're going to be like swallowing the food, swallowing the food, swallowing. You're going to want to keep coming back to the chewing part. Like if you can't swallow, what happens? If you can't swallow, you've got to go back and chew some more. You spit that up and chew it just like a cow. In the same way, you watch the lecture, get some confidence, start chewing, try to swallow. If you can't swallow, come back to the lecture and try again. Keep chewing until you mush up these principles enough so you can swallow them down by doing sufficient homework. Got that? All right, so we've also seen now, we had this equation. So it's not like this equation is one that is a universal equation. This is an equation, one relationship between what x might be and how it might change as a function of time. If we plotted this, if this were our equation for position, so we can see x instead of s, which means we're on the x-axis, and we know that it's changing with this relation of time. We could plot out that relationship as we see in this first figure, the position with respect to time. We could actually take the derivative of that and we'll have the velocity and plot that in this second plot. If we take the derivative of the velocity, we now can plot that. You'll notice it's now got a gradient, a constant change. Another thing we're going to notice, we're going to talk about briefly, since our velocity is dx dt, that's the change in x with respect to the change in height. All that means is, that means the velocity is the slope of the x curve. If we plot x on one axis and t on the other, then whatever point it is, that's the position with respect to time, the velocity is just the slope of that curve. Okay? You'll notice here the slope of the curve here is 0. The slope of the curve here is also 0. You'll notice the slope is changing from positive to negative. You notice it looks like it's still increasing. Well, the x position is still increasing. You'll notice it's increasing fast, and then it's increasing at a slower, it's decreasing. Its position is changing less rapidly, which means we're actually getting a negative velocity, right? Or our velocity is a negative, but we're slowing down our velocity. You see that change from a speeding up to a slowing down that curve. If you look at the slope of this, draw the slope, and then until it becomes 0, that's right there, and then it slows down faster and faster, or becomes more and more negative. And our once again, in the same way, the acceleration is the slope of the velocity curve. So the slope here is positive. The slope here is 0. The slope here is negative. You see that? Okay. All right. Actually, the slope is, we're seeing that the slope, it's decreasing the whole way. Well, we get a positive acceleration because that's the slope, right? Positive acceleration. Then from there, it's negative, and then it gets more and more negative as we move on. So if we want to know what the position is, or the velocity is, or the acceleration at any given time, we then select the appropriate equation for position, velocity, or time, and just plug in the values of time. Since the x is a function of time, we can plug in time to get x. Since velocity is a function of time, we can plug in time to get v. Since acceleration is a function of time, we can plug in time to get acceleration. We can also plug in, and then having the velocity, we can actually calculate what the position is. Or we can actually use position to do this. You'll notice here also, we're going to talk about this in a minute, acceleration not only is dv dt, it's the second derivative of x, which means we actually could look at the second derivative. That's actually not the slope anymore, but it's the change in the slope with respect to time, which gives us our acceleration, okay? If we had a different timestamp we wanted to evaluate, we just plug in those values. Got that? All right. So we have the basic equations, and we look briefly at what happens when our velocity is constant, when our acceleration is constant. Whenever that happens, you should go, woohoo, because things get a little easier when those things are constant. In fact, it'll be even easier when they're 0. Okay? So if our dx dt, that's our velocity, if that happens to be a constant, then remember the velocity comes out of the integral, and we get these relations, right? This dx, the integral of that is just x, but remember we have the limits of integration. We're going from x0 to x, which means x minus xo is what that x becomes. Here the v is unchanged, and inside here we just get a t, which is t minus t0, right? So what's shown as a t down here is just t minus t0 next to the v, okay? And we can rearrange that by bringing that xo to the other side, and we say that x equals xo plus vt. When is this true? Only if the velocity is a constant, because the velocity came out of the integral, okay? One of the common mistakes students make is treating velocity as constant when it's not, or treating acceleration as constant when it's not. The next subcategory, when we have uniformly accelerated rectilinear motion. Okay, this sounds like a big word. Uniformly means it's the same, gonna keep, however it changes, the same. It's being accelerated. We're talking about acceleration. Rectilinear, which means straight line, and motion, which means it's not going to be in the same place when we look later, okay, if we blink. If the forces applied to a body are constant, remember, we talked in our first lecture about F equals ma. If we sum all the forces, that gives us an acceleration. If the forces are constant, okay, then you're going to have uniformly accelerated, which means the acceleration is not changing. If the forces are constant, okay? If you have the forces are constant, you're going to get acceleration. If we have free fall means we've got the only force on us is gravity, so we're getting a constant acceleration of gravity. Now that can be affected by drag, but if we neglect drag, then it's an example of constant acceleration. All right, so for uniform, so remember, these are equations. Remember, dv dt equals a. That's true, but if it happens to be a constant, we get this relation over here, the simpler relation. This is true, dx dt, and if our acceleration happens to be a constant, then we get this relation here. And this is true, but if our acceleration is constant, then we get this relation here. These three equations are only valid if we have constant acceleration. You've got to be careful to figure out, do I have constant acceleration? Can I use this subform, or do I need to do the integration myself? Okay. This is a cool little graph. This is showing acceleration versus time from a round, allegedly from a round of boxing, from a head impact. Those of you that are hit in the head know how this feels. In fact, I still got the 3 staples in my head from the from the lift at the snowboarding just last weekend. So what we see here is a function of time and how that force changes because your head was resisting motion, probably is why that force built up. And that's giving you an acceleration or an acceleration deceleration. This is from a head impact. Kind of cool stuff. It's a lot easier. It doesn't hurt nearly as much looking at this graph as it does when you're popped in the head. All right. We can also do graphical solutions. Remember, we talked before, if this is the plot of the position with respect to time, we've got x here, so we're talking about position on the x-axis, but it really could be any position. It could be y, it could be z, or just s. If we plot position versus time, that graph will give us, at any point, we can calculate with that time value, we can figure out what the position is. Also, if we look at the slope at any point, that's going to give us the instantaneous velocity. If we then plot the velocity curve, the slope of the velocity curve is going to give us the acceleration, instantaneous acceleration, okay? So we can actually look at the slope, and that tells us from our derivative equations, relates the one to the other. We can also look at the area under the curve. Remember, when we're integrating, we're summing up over some difference in time. So if we look at the acceleration time curve, between two time periods, the area under that is going to be our change in velocity, because if we integrate the acceleration, we get the velocity. So looking at t1 to t2, that area under that equates to the change in velocity. This can be useful for graphical solutions, and sometimes the principle can help us to solve other problems. If we look at the velocity time curve and take the area under it, we're going to get the change in the acceleration. That's going to give us our, right? Between that, we're going to get our change in position is going to be from t1 to t2. So we can look at position curve and get our velocity, or the area under that is going to give us the change in velocity. x2 minus x1 is the integral. Looking at the area under the AT curve, we get our velocity. Area under the VT curve gives us our position. Okay? So these are our key relations. And sometimes, so velocity is just dx dt, or we could call it as generally ds dt. S is just our position variable. We can also call that s dot. Whenever you see this s dot, we did that in calculus, remember? Used a dot as a shortened way of saying the derivative of something. In this case, what we're taking the derivative with respect to can be a little tricky, but often this is talking about the derivative with respect to time. So we could call this A is just the s dt, which is just s dot, the v dt, which is v dot. Alternate, we can write in this v dv equals a ds. We can take either the derivative or the integral. And if we have a special case of constant acceleration or velocity, we get these equations down here. These are the equations we're going to be using. When we do our homework, what we're going to want to do, we're going to look at a problem, I don't know how to solve this. And what you do is start writing equations. Okay, so I got these equations. It's all these same equations. Which one of these apply? Do I have constant acceleration? Do I have constant velocity? Then I can write those as well. Which variables do I have? And you're looking for which equations, use the variables that you have, and also have the variable that you're looking for, because you want to be able to calculate that. So you'll be looking for which equation have the variables you want and the variables you have, so that you can orchestrate calculating a solution from the information provided. And it takes some practice to get good at this, but it's not nearly as hard as it seems. Let's look at our first example. This is a very common example. You can see this a lot of different ways in a lot of different dynamics courses. We have a ball tossed out a window. It's tossed with a vertical velocity. So the pictures are a key, an important key to how these things work. This picture says we're at a position. We're 20 meters off the ground. Our origin is down here at 0. That means S down here is 0. Position S up here is 20. Instead of calling it S our position, we can use y, since we're talking about a vertical position, rectilinear motion in a vertical direction. So we can say y initially, or y of 0, is 20. Eventually, this ball is going to hit the ground, so y final is going to be 0, okay? But some idiot threw the ball upwards. Now, fortunately, it's straight up and not off at an angle, so it's just going up. Now, when this ball gets thrown, that means we're going to have a velocity at position 0, x0, or y0, remember, at 20. y0 is 20. We also have an initial velocity, v is 20. So actually sketching this, if it's not already sketched for you, sketching this out can really help. Draw a horizontal line for the origin, show the position of your ball, show the dimension, 20 meters in this case, show your velocity. It looks like it's tossed upward, which means it's got a positive velocity going upwards. That's 10 meters per second. Okay? So your initial velocity, v0, that's 10. So s0 is 20, or y0. v0 is 10. And now we're going to say, okay, then what happens? Well, any of these problems that involve throwing something and it hitting the ground is going to utilize that initial position. It's going to use the final position. It's also going to utilize that point when you stop moving. Because if you throw the ball up, what goes up must come down. It's going to come back down. Why? Because we have a constant acceleration. That constant acceleration, that ball has gravity acting on it. Don't forget that. Your gravity is pulling the ball. It's accelerating the ball toward the center of the earth as soon as you release it. So if you throw the ball upwards, you have initial position, 20. You have initial velocity, 10. You have initial acceleration, which is a 9.81 meters per second squared, but that's downward. That's a negative value. It's pulling you opposite to your positive y direction. So that's going to be negative. Okay? You have to get these right. Then, with that known, you know you're going to go up, and at some point it's going to stop. And then it's going to start. It still it's accelerating downward, but because accelerating downward, that acceleration is going to slow it down until it stops. And then it's going to be speeding it up until it drops. Okay? So we're going to utilize all of those pieces of information. What is the velocity initially? What's the position initially? What's the acceleration initially? Notice we're going to have different positions. We got position initial, which is 20. Position when it changes direction, we don't know what that is yet. Position when it ends, we know that's 0. We have initial velocity 10. We have a velocity at the highest point, which is 0. And we have a final velocity, which we don't know. We have a acceleration initial, which is negative 9.81. It's negative 9.81 still when it stops moving upwards, and it's negative 9.81 when it hits the ground. So those pieces of information. The hard part of this problem is learning the ability to recognize all the myriad of pieces of information. We have 3 positions. 2 of them are known, 1's unknown. We have 3 velocities. 1 of them is known. 2 are known, the initial and the top one. We have 3 accelerations, all known. Okay? We're going to be orchestrating those pieces of information with the equations we have in our holster. You could think of these ideas, the equations, calculus as your gun, with all these little bullet holes of all these little equations, little variants of the equations, where you pull those out, stick them in your gun, and you're going to, you can think of your gun as your calculator, and these little bullets are the equations that you're feeding into your gun to solve these problems, okay? So this is our redrawn problem. We have a constant acceleration. Since we have a constant acceleration, we can use these constant acceleration equations. We could have started with the dv dt equals s, right? V equals dx dt, and a equals dv dt, and integrate these. Or you can just say, wait a minute, I know this is constant acceleration. I'll just grab the thing that's already been integrated for me. So s equals so plus vot plus 1/2 at squared. That's always true for constant acceleration. And velocity equals velocity initial plus acceleration times time. That's always true if we have constant acceleration, okay? So we're going to use these. We're going to insert these, fill these with our constant. Remember, we're given 9.81 is our acceleration downward. It's negative, actually. We have our initial velocity, which is positive. We have our initial position, which is 20. We have those other pieces of information. So we're going to say, okay, and what are we looking for here? We're looking at our velocity and position as a function of time. Mainly, we're generally going to look at what's the position at the top before it goes down. What is the speed at the bottom? Okay? Let's practice. What's the speed initially? Positive 10 meters per second. What's the acceleration initially? Negative 9.81 meters per second squared. What's the acceleration at the top? Negative 9.81 meters per second squared. What's the acceleration at the bottom? Negative 9.81 meters per second. Okay. How about the velocity? Plus 10 meters per second. 0 meters per second. Unknown. How about position? 20 meters. Unknown. 0 meters. Those we're going to plug in to solve this puppy. Okay? Let's check it out. This is what we're given. Sketching this is critically invaluable, right? Given on your paper, sketch out the problem. Even though you can read, you can see it on your paper, sketch it here. It will help to rewrite these, and it doesn't take long. You need to develop the skill of sketching. Right or fine. What are we looking for? We're looking for these things, and we're going to work through these systematically. And then you start solving. This is our equation. V equals VO plus AT. All right, at the peak height, we know the velocity was 0. So the velocity initially is 10. The velocity at that peak height, we're going to look at that second position, is 0. The acceleration is negative 9.81. And the time is what we don't know. We can solve for time. Bang, got that. Carry enough digits, more than you need, so you don't have unnecessary error. Okay? Next, for our next part, we can say, okay, use that other equation. S equals the initial position plus the initial velocity times time minus 1/2. This is actually plus 1/2 gt squared, but our g is negative, which introduces that minus, okay? So our initial position was 20. Our initial velocity was 10. Our time at that point was just calculated. And so now we can calculate what the position is at the top. 25.1 meters. So it traveled 5.1 meters upwards before it stopped and changed directions. Now we can calculate our velocity then. We can actually write our velocity equation again. It's just VO minus GT, right? We could just write that. And our remember our position was just 20 plus 10 meters per second T. This is just writing those equations out. And now we know it, when the ball hits the ground, we're going to use this last equation again. Now that S equals VOT minus 1/2 GT squared. We know the final S is 0. The initial S was 20. The initial speed was 10. We don't know the time when it hits. Our acceleration is constant, 9.81 down, but now we've got over 2, that 1/2 thing. We can now are going to end up getting, we can solve this with the quadratic equation. We get 2 solutions, one of which is meaningless and the other one makes sense. You can't go back in time. Surprise, surprise. So at 3.28 seconds, we're going to get impact. If we want to know the position, we already know the position. If we don't know the velocity at that, we can actually just plug that into our velocity equation and we get the velocity. Notice the velocity at final is negative because it's acting downward. Or initially it was going upwards, now it's going in the other direction. The signs are critical. Where is our position? Are we positive or negative position or 0? What is our velocity? Is it in the positive direction or the negative direction? What is our acceleration? Positive direction or negative direction? You can do all this correct, plug in the wrong sign on the acceleration, and it's going to all be wrong. Plug in the wrong sign for the velocity, it's going to be wrong. Got to be careful. A major piece of engineering is just attention to detail. Here's another little example. We'll move a little faster here. If you want to spend more time in these examples, I recommend you get one of those textbooks I mentioned at the beginning. I actually have a few I don't think I did any dynamics books reviews, but I have, for each of my classes, I have a few book reviews that I've performed and put a little YouTube video. I'll try and get those out soon for dynamics. Okay, let's just say that we have another particle and its motion is defined by this equation. So we have the position with respect to time, and this is the equation that we're given. Okay, and the units are inches and seconds. Okay, we want the position, that's the area of this equation, the velocity and the acceleration when t equals 1. Well, to get the position at t equals 1, all we got to do is plug in t equals 1 to this equation. To get the velocity, we first have to differentiate this and then plug it in. To get the acceleration, we need to differentiate the velocity and then get it. So it's done like this. This is our x, the derivative, and the second derivative. Plug in our time, bang, bang, bang. Show appropriate significant figures. In this case, this starts with a 1, so it's 4. This starts with a non-1, so it's 3 significant figures showing appropriate units and direction. Okay? Here's another one. We got a stone. It's thrown vertically upward from a point on a bridge that's 40 meters above the water. This is very similar to our first problem, right? We know it strikes the water 4 seconds later. Okay? So we have a different piece. We got that initial. It's thrown from a bridge at 40. It strikes the water 4 seconds later. We want the speed with which it's thrown upward. So now we don't know the speed. We do know the position. We also know the acceleration, right? 32.2 feet per second squared. Or actually, we're SI, 9.81 meters per second squared, downward, negative. At the top, it's thrown vertically, right? At the top, we still have the same acceleration. We don't know what the height is, but the velocity is 0. And when it hits, we know it's 4 seconds later. We don't know the velocity. We do know the position, and the acceleration is still negative 9.81. So we write our equations and systematically solve it. There's our initial speed by just plugging in that 0, and bang, we've got it. Okay? Here's another example. Now we're horizontal. We're talking about rectilinear on a horizontal axis. Great. We're traveling. There's our initial velocity, kilometers per hour. Don't forget, you need to change this to meters per second to do this, right? You can't leave this kilometers per hour. You want those equations for relating your kilometers to meters and your hours to seconds. Okay. We have a traffic light too. Now this looks tricky, but actually all we got to do is write down what do we know, what equation do we have, which equation ties these pieces together. Which equation takes the information I have and also has the information I need. So we have a motorist. We're at 54 kilometers per hour, which we're going to write as meters per second. We see a traffic light, and the distance is 240 meters. It's timed, let's say she knows that it's timed to stay red for 24 seconds. That means we know from here to here she's got 24 seconds. The change in time is 24. And the motorist wishes to pass without stopping. Okay, so all we've got to do is figure out, for us to go 240 meters with a starting speed of 54, what acceleration or deceleration in this case will make us not pass that before 240, and then also the speed of the car as we pass the light. So we know our initial position, we're going to call that 0, and we know our initial velocity. We also know our distance that we're going to go, right? So we can use this equation, x, which we know is 240, xo, which is 0, vo, which is 54, and we know time for both of these is 24. All that's left to know is a. We just solve for a, and we've got it. We need to decelerate at minus 0.417. Unfortunately, there's no little button on the car to punch in minus 0.417, so she's going to have to apply the brake pedal to do this. We then can use that acceleration in this equation, since that is going to be a constant acceleration, that's what we decided we're looking for. We can plug in that constant acceleration and calculate what our initial, what our velocity is when we pass through. So remember, v equals vo. So vo is 54, and the final v is 54 plus AT, but A is negative, remember? And we can calculate what that value is. Here's another one. This is similar to our first and third or something problems. We have a group of students launching a rocket in the vertical direction. They figure out the altitude is 89.6. It lands 16 seconds later. And the descent parachute failed to deploy, so it falls to the ground, assuming our constant G pulling it downward. This is the same problem, we just have different pieces of information to plug and chug for. We look at our three positions, the initial, that point where it starts dropping, and the final, and we can plug and chug like that. Got it? Okay. So you should be a little excited, a little confident, and a lot scared. You've just finished the chewing. Now you need to go find some problems to practice on. If you're in class, use your class textbooks and your class problems. If you're an industry professional or you're not in a class, you don't like your class, you got a class that doesn't have great problems, get one of those books I talked about and practice on those books in the corresponding chapters. The more practice you do, the more this becomes yours. You can almost dial in your grade, whatever grade you want to do based on how many hours you're willing to spend. Everybody's not the same. Some students will only need maybe 3-4 hours to master these ideas. Some students might need 20 or 30 hours to master these ideas. But you can get any grade you want if you're willing to invest the time that you need in the swallowing, and that's the homework part. Enjoy.